Alright, so we've got a ski patrol, a rescue sled. Somebody's had a very bad skiing accident. We have a coefficient of friction. Alright, so we have some questions. What is the work done by friction? What is the work done by the rope? What is the work done by gravitation? What's the total work done? Okay. So work is equal to a force applied over a distance. All right, so your book has a pretty good explanation of how we get this form. But one thing that it's important to note is that only the part of the force that is parallel to the movement counts. So frequently we write F delta x cosine theta, where theta is the angle between F and delta x. All right. So for here, we've got a few plug-in chugs to be done here. The first one is how much work is done by friction. Well, before we can talk about the work done by friction, we need to know how much frictional force there is. So this convenient diagram that they've given us here actually leaves out the normal force, which is something we're going to need. And let's define our coordinate systems like this, so that up the slope is the positive x direction and normal force is the positive y direction. Also, pretend that I can draw straight lines with any regularity. So with that said, we can define our all of the vectors that are important here. So for our forces, our tension is only in the x direction. Our friction is only in the x direction. Normal force is, of course, only in the y direction. And weight is a little bit of this, little bit of that. Does anyone need an explanation of how we got this this breakdown here? Okay. We also, the distance that we're moving up the slope is 30 meters, and with the way that we have defined our coordinate system, that's going to be 30 meters in the x direction. Okay. So with that said, now we can start computing the work, the work done by these various forces. Since the displacement is all in the x direction, only the x component of these forces are going to count for doing work. Oh, actually, hold on. We actually need to calculate how much normal force there is, and then we'll be able to. Then we'll be ready to move on. Okay, so we're told that we are moving at a constant speed, which is our keyword for acceleration equals 0. So if we consider the sum of forces in the x direction, those sum of forces should be 0. And that's going to be equal to t minus or plus mu n minus mg sine 60. And in the y direction, the sum of forces should also be 0. And we will have in that direction n minus mg cosine theta, or cosine 60 rather. Which lets us immediately say, well, the amount of normal force we have then is mg cosine 60 so maybe we rewrite our frictional force. It's mg cosine 60 in the x direction, 0 in the y direction. Now let's go back to our x direction, solve for t. So t equals mg sine 60 minus mu mg cosine 60. Everyone with me so far? Yes? That's right. So the sum of forces is 0 because we have no acceleration in the x direction. Which we know because the problem said that there was constant speed. Yeah, that's exactly right, Yusuf. Constant speed is our clue. All right, so we can get numbers for a lot of these forces now, which I'm going to take a moment to do. So the weight, right? So the weight of this, it's a 90 kilogram person plus sled. So the weight in the x direction is 900 times sine 60, which is 779. And in the y direction, get 450. Normal force is equal to mg cosine 60, so that's going to be 0 in the x direction and 450 in the y direction. The coefficient of friction is 0.1, so 0.1 times 450 is 45. And then the tension is the mg sine 60, which is 779, minus the frictional force. That's going to be 734. Okay, I added the negative sign on the delta x because I realized we're going down the hill, actually, in this problem. Alright, so far this is all chapter 5 stuff. Now that we have all this, we can do work. So the work done by friction is this 45, right? They're all going to be force times parallel part of the force times the displacement. So the x part of friction is going to be 45. And delta x is minus 30. So we get negative 1350 joules. What does the negative sign on work mean? Right? It
Done
means
system, right?
yeah, that's right. So energy has been lost because of this work. So energy has left the system due to friction, um, which yeah is what we expect, right? Friction slows things down, so it is going to bleed energy away from any system it's a part of. B, how much work is done by the rope? So the work done by the tension is going to be equal to 734 times negative 30. So that's a really good question about the theta. So is theta 180? Here, so the cosine of 180 degrees is minus 1, right? For me here, I've let that minus 1 be carried in this negative sign, right? So that if we have forces and displacement that are in opposite directions, that will lead to a loss in energy, which is a negative work. Um, and then if they're in the same direction, they're both negative. The negative signs will cancel out and you'll get positive work done. So is work done through friction always negative? Yeah. Friction only subtracts energy from a system. For sliding, right? So you can make the argument like if you're running, right? It's actually the friction between the ground and your shoe that causes your forward movement. But if we're looking at a thing that is sliding, right? Then friction is going to be leaching energy from the system. All right. So the negative sign that would come from cosine 180, I have let it be carried at, here in the negative direction here. The victim. The accident victim is going down. We are multiplying by negative 1, but we got the negative 1 um, from our coordinates. Right? So this theta here, right, is the acute angle between the force and the displacement. So yes, the f and delta x in this case are in opposite directions, so the angle between them is 180, but the acute angle between them is 0. And we let the negative sign be carried by our coordinate system. There are texts who do not present it like that and say, and they put absolute value signs on f and delta x and then let theta be all the way up to 360 degrees. All right, so work done by the gravitational force. negative 779 times negative 30. So this is going to be a positive work, because our two negative signs will cancel out. And the total work done, that's right. So it's moving horizontally. So the y portion, not moving horizontally, it's moving in the x direction. So forces in the y direction do no work because there's no movement in the y direction. So the total work done is 0 here. Which we could have figured out way over here, because if there's no net force in the x direction, there can't be any net work from the x direction.
So I kind of just have like a lingering question about that.
Mm-hmm.
When it's asking for total work, is it referring only to the x direction or also the y direction?
So if we had movement in the y direction as well, we would also be adding up the work from those directions.
Okay, and why would it be 0 in the x direction if it's moving?
It's moving, but at a constant speed.
Okay,
So 0 acceleration.
that makes sense. Thank you.
You're welcome. So yeah, so basically we've come at this problem from two different ways. We've considered it with work, we've considered it with forces. And yeah, so even though each individual force may do some work, positive or negative, the total work done has to be 0 because the total net force is also 0. All right. Any other questions on this problem? That was awesome. I'm glad you enjoyed it. We had a request for Chapter 6, number 34. All right. So some gravitation questions. So we've got the sun over here. You've got the earth over here. And you have the moon. So calculate the magnitude of the acceleration due to gravity on the surface of Earth due to the moon. So remember, our force of gravity, our general force of gravity, is equal to gravitational constant, product of the two masses in play, divided by the square of the distance between them, and then the negative sign to show that it's an attractive force. And this part, the gm1 over r squared, this is our little g, our acceleration due to gravity. So if we plug in the values for mass of the Earth, radius of the Earth, g comes out to be 9.8. Well, basically, we want to. This question is asking us to play with the numbers. The acceleration of gravity due to the moon and the sun. So the moon is somewhat smaller than the Earth, and it's much further away from us than the Earth is. So we would expect the effect due to the moon to be relatively small. But let's see what we've got here. So for A, the gravity from the moon is equal to gravitational constant, which is how much? So g is only 10, like little g is 10 near the surface of the Earth. Big G, the universal constant, is quite small. It is 6.67 times 10 to the minus 11.
For all the problems, that would remain the same. It's a constant for
the universe.
For all the universe. Okay, perfect.
Yeah, it's your first glimpse at something deep and universal. We don't actually have that many universal constants to play with, right? But the strength of gravity is one of them. So we have 6.67 times 10 to the minus 11. And then also in the numerator up here will be the mass of the moon. Anyone know what that is offhand? It's alright, I had to look it up too. It's 7.34 times 10 to the 22 kilograms. And then in the denominator, we have the square of the distance to the moon. Which is about 384 million miles. Does the textbook actually say that? No, but it's implied. Well, I think access to the internet is implied. So this distance, by the way, it's not from the surface of the Earth to the surface of the moon. Technically, we should also be including the radius of the moon, right? Because this r in Newton's law of gravitation is the distance between the center of masses of the object. However, the radius of the moon is real small compared to the distance between the Earth and the moon. Right? So the radius of the moon is only like, I don't know, 700 kilometers or something like that. So it's less than 1% of the Earth-Moon distance. So I feel safe in neglecting both the radius of the moon and the radius of the Earth. But if you wanted to get pedantic about it, right, you would have to include the radius of the moon in this r here, and you would also, if you were on the other side of the Earth, you would have to include the diameter of the Earth as well. Like I said, those numbers are going to be like 1% of the Earth-Moon distance, and we're going to square them, so the difference will end up being 1% of 1%. Okay. This 384 million number, it's inconvenient. I'm going to rewrite that in scientific notation. Okay. Everyone's good on scientific notation, right? So we don't need a super accurate number here. We can afford to do some rounding. First thing I'd like to do, actually say, you know what, 3.84, that's basically the square root of 10, right? Square root of 10, approximately 3.84. Close enough. So when we do this square in the denominator, we're going to get something that's like 10 times 10 to the 16. 3.16 close? Yeah, it's close enough. So this denominator is really going to be 10 to the 17, more or less. So then if we count up powers of 10, we have, in the numerator, we have a 10 to the minus 11 and a 10 to the 22. So that gives us a 10 to the 11. And then divided by a 10 to the 17, so we get something that's like times 10 to the minus 6. And then we can do this multiplication in here. 6.67 is approximately 7. 7.34 is also approximately 7. So we multiply them together, we're going to get 49, which is approximately 50. Better put a heavy approximate sign there. Yeah, ain't nobody got time to fish out a calculator. So we got physics to do. And since we're talking like astronomical distances, even if we're off by like a factor of 2, that's still pretty okay. It's all right. So that's going to be approximately the acceleration due to of gravity due to the moon. I'm going to erase some of this. Bring up the this number so we can have room to do the sun. See, Yusuf plugged in all the numbers and he got 3.3 times 10 to the minus 5. So I think that approximation's pretty darn good. I was only off by 50%. All right, so we're going to do this. We're going to do the same thing for the sun. The sun is a lot further away from the Earth, but it's also a lot bigger. So the sun is 2 times 10 to the 30 kilograms, give or take. We only consider one of the masses? Yeah. So if we wanted the force between two masses, we would consider the product of both masses. If we want only the acceleration due to the gravity from one mass, then we just need m1. So the distance between the Earth and the Sun is defined to be 1 astronomical unit. It's also approximately 8 light minutes. But the more useful unit here is that it's also 150 billion meters. All right. So we're going to play some of the same games here. 1.5 is approximately 1.4, and 1.4 squared is 2. So this is going to be like 2 times 10 to the 22 in the denominator, and that we can actually cancel that with that 2 up there. So then we collect powers of 10, and we get 10 to the minus 11 times 10 to the 30, so that gives us 10 to the 19 overall. And then divided by 10 to the 22, so we get something times 10 to the, like, that's 10 to the minus 3. So this is approximately... So even though the sun is way further away than the moon, it actually has 100 times more of effect on our gravity than the moon does. Well, it can't be times 10 to a positive number, because it has to be smaller than 10, right? Since the acceleration due to gravity on the Earth's surface is 10, and the effect of the sun has to be smaller than that. You're making me pull out a calculator. How dare you? In our picture, the green is the moon. That is correct. Alright, so when I actually use a calculator, I get 5.93 times 10 to the minus 3. Again, I think my approximation was pretty okay, considering that I didn't have to stop and pull out a calculator. What kind of calculator are you using, Yusuf? Oh, there's your problem. If you need a calculator that is more powerful than like the simple scientific calculator that comes on your phone, then why stop with the TI-84? TI-84. Oh, pumpkin. Pardon me 1 minute, folks. My lovely wife has brought me a coffee and a muffin. Thank you so much. Yes, you can have it convert to scientific notation. We live in the future. Yeah, high school is generally where people get into the bad habit of using a TI-84. Did you know that there is a free app on Android phones which emulates a TI-84? So if you really, for some reason, wanted a TI-84, you could download a free app and get all that functionality, or you could pay $100 to get the actual calculator. Up to you, I guess. The iPhone has something like that too. I just forget what it's called. Um, but Mathway is also fine. Um, so obviously I like Wolfram Alpha a lot. I also use Desmos pretty frequently. So there we go. I feel like Desmos is just so superior to any functionality on the TI-84. Um, Wolfram Alpha will actually even do integrals for you if you need to do something like that. Here we go. There's the integral, the plot of the integral, series form, Maclaurin series. It's pretty good. And if you need the step-by-step solution, $5 a month will get you a subscription. So this is a super useful website. Yeah, they charge for the step-by-step now, but it's not very much. So it was free for a while. In fact, if you bought their app before they introduced Pro, you can still get free step-by-step through the app. But the app is, I think, no longer available. So you have to have already bought it. So, Yusuf, you were actually watching the Walter Lewin playlist? That's fantastic. Walter Lewin is super smart, and as much as I think that I'm a great instructor, he is a much better lecturer than I am. Also, he's got this amazing physicist hair, which you just can't, like, there's no substitution. And so he integrated force to get the formula for work. And yes, that is actually the definition for work. So work is the integral of force along a path. But since in this class we're not really doing integrals, we just restrict ourselves to the case where the path is a straight line and the force does not vary over the course of that straight line. Can you ask about an equation you found in the book, which I used for question 5, Rx equals V? Yeah, so that, yeah, so several people used that, and when I graded the exam, I said lol magic equation or something like that. Because nobody actually mentioned what it was, where they found it, why it was correct. So the equation that a lot of people used, like started with, they said R equals V naught squared right. Is that right, Jolene? Yep. You're as per the book. I actually haven't gotten to your exam yet, but if you at least mentioned that it was in the book, I think I would give you credit for that. But what is the R in this case? Like what does the R even mean? It's the range. Yeah. This range, right? If we look at our kinematic equation, right? This range is just our x final minus x initial. And the way we get this, right, the place this equation comes from, right, all it does is save you a little bit of algebra. So, oops. So it saves you a little bit of algebra, but it loses you a lot of understanding. If that makes sense. So you got it from the Glazer Tutoring Company? Yeah, that's a decent YouTube channel. My favorite channel like that is actually the Organic Chemistry Tutor. But yeah, Glazer is also fine. And I know that all of you are going to be using YouTube channels and Chegg and whatever else to get your solutions. What I want to see when you turn in work is I want to see that even if you got the solution from somewhere else, that you understood where it comes from. Right? So anyone who just quoted this formula and said nothing about it, they lost points for that. So the where this comes from, if we consider the x and the y directions, just like we have a dozen times. In the x direction, our initial x right here we're looking at like a ballistic path, like so.
I pasted the question in case you want to reference it.
Oh, I appreciate that. Let's stay general for the moment. Like it could be any path. Right? It could be any setup. But in general, with our projectile motion, we're going to define the origin to be where the arc started, and if our final position is also at height 0, but at some distance x, right? See, we've already made an assumption, right? This formula is only valid if you end at the same height you started at. But in that case, we come from our first kinematic equation. We start at 0. We have some part of the initial velocity in the x direction. We have 0 acceleration in the x direction. In the y direction, we're going to end up at height 0. We also started at height 0. We have some amount of the initial velocity in the y direction. And we also have some acceleration. So if we take the x direction and we solve for t, and then we take that t and we plug it in from our y direction equation. So we get 0 equals v naught sine theta x over v naught cosine theta minus 1/2 g So in this first term, v naught in the numerator and denominator cancel. Sine over cosine is tangent. So we get x tangent theta minus, and then over here, x squared right from the squaring here times g over 2 v naught squared cosine squared. Factor out an x. All right, so we have this expression factored into two pieces, and these two things multiplied together equals 0. What does that mean about the value of these two factors? So, Jasmine, you're close. Not both equal 0, but we know that at least one of them equals 0. Right? If one or the other equals 0, then the product of them is going to equal 0. Does that make sense? So the first, the first option, x equals 0, is not very interesting, right? And that's actually not what we're looking for. So if x equals 0, that means that the projectile hasn't gone anywhere yet. So even though x equals 0 is a solution, that's not the solution we want. The solution we want is this thing in the parentheses equals 0. So we have tangent theta equals xg over 2 v naught squared cosine squared theta. I'm going to give myself some room to finish working this out. So if you solve for x, right? There's some easy bits to this, right? So if we want to solve for x, we need to divide by g, we need to multiply by 2, we need to multiply by v naught squared, we need to multiply by cosine squared. Okay. That's not the formula we started out with, right? How do we get to the formula we started out with? Right? Does this equal trig identity? Okay. Talk me through it.
I know that there is a sine, and I know that cosine squared is the same as sine 1 plus sine squared of theta, I think.
1 minus sine squared, but yeah.
1 minus sine squared. Or we can change the tangent into sine over cosine.
Yeah. Let's give that a try. Because if tangent is sine over cosine, then the over cosine bit will cancel with this cosine squared. How do we get to the equation in green from that?
It's also another trig law or whatever it's called when we see sine multiplied by cosine, it's the same as sine 2 theta, right? Because when we break it down, I don't know if I'm remembering my pre-calculus correctly, but it's let me just 1 second. That it's sine times cosine plus, I don't know, we add them and multiply them, something like that, but I could be wrong.
No, you're on the right track. So let's take a trip to my favorite web page. Everyone remember what my favorite web page is? Yeah, you got it. It's just so beautiful. It's just so beautiful. What we're looking for are the double angle formula. So, yep, sine 2 theta is 2 sine theta cosine theta, or we can write it as 2 tangent theta over 1 plus tangent theta. And then there's several more for cosine for the others. So yeah, so we're looking for the double angle formula to finish this off. So, how many of you could have reproduced this work on your own? Felt confident that you could derive the formula in green from the kinematic equations? Okay, so if you'd had an hour, you could have done it. So all of you used this formula. Did any of you know where it came from before you used it? And that's my issue with magic formulas. Right? If you just see something like, oh, that seems like maybe it applies to this situation, but it completely obscures all of the physics that's happening. Right? It's just this magic formula. You don't know where it comes from. You don't know where it goes. You don't know where it comes from, Cotton Eye Joe. And it doesn't actually advance your understanding at all. Right? And I want to say deriving it, like getting it into this compact form, actually takes way longer than just doing the problem from the kinematic equations, right? Like if we take a look back, if we're here in blue, right? We're only like 2 lines from finishing off this problem. Right? Because we can plug in all of our values at this point, right? Solve for t, plug in all our numbers, plug that into the y equation, boom, done. And doing it that way, like we take doing it that way makes it clear what physics is going on, right? It's just projectile motion. It's just the kinematic equations. Nothing special to see here. And then leverages a little bit of algebra skills, which, we all have.
Dr. Wolfs, may I ask you a question really quick?
Of course.
So about the exam, right? So I think you said it was going to be out of 30 points, if
Yep.
I'm remembering correctly.
And then I changed it to 36 so I could give more partial credit.
Got it. Also, so like if you're gonna, so right now I know some people have been saying that you've been entering grades. Is that the grade like before the curve or after the curve?
Before.
Okay, thank you.
So curve, I won't handle the curve until the end of the semester, probably. Okay. Some people have gotten their grades back. I have finished grading 15 exams out of 80 students. 83 students. So most people have not gotten their grades back. Jasmine, of course. Ask away.
Okay, I would like to go over chapter 20 or question 22, and also I wanted to ask you something. So, is so for these problems, is like final velocity like always gonna be like, I guess like positive for these problems,
It's
or initial velocity?
it's positive if you define that direction to be positive.
Okay, got it.
So which one from 34?
I'm sorry.
Or sorry, which one from chapter 7? Was it number 34?
22.
22.
I think. Sorry. Yeah, 22.
All right, we'll see you later, Jolene. Okay. A large spring bumper. Okay. Trains are one of the few things I can draw, but subway trains I cannot draw. In my mind, all trains are steam engines. So we have a spring in front of this train, and we'll call this situation A. And then in situation B, we have the same train, which now has a squished spring. And no velocity. And the squish on this spring is 40 centimeters. And we'll go ahead and say that to the right is the positive direction. Okay. So we're going to be using the work energy theorem because that's what we're going to be using all chapter. So work is caused by a force over a distance which causes a change in energy. Okay. The tricky part to this problem is actually drawing the boundary of what we mean by our system. Wait a minute, hold on. Has my virtual background been off this whole time?
Yeah. You just noticed?
I just noticed. Well, at least I made my bed.
It's okay. Yeah.
And there's my dog.
Aww.
Kaylee. Come here, Kaylee.
She's really cute.
She is very cute.
Where's your cat?
They're around. My wife and I have 5 of them.
Oh, I just have one.
All right. There we go. So unprofessional. All right. Yeah, my wife and I both had a totally normal number of cats before we got together. And then when we got married, we had an abnormal number of cats.
Oh, got it. That's funny.
Okay, so work energy theorem, boom. The key is defining what the system looks like. So if we look at, if we consider just the train to be the system, then the force exerted by the spring on the train is an external force that does work, right? But the force done by the spring changes as the spring gets compressed, right? So the more you compress it, the more force it exerts. So to deal with a changing force, we would have to use calculus. And we don't want to do that, so that option is right out. What we want to do instead is say, actually, our system is this train and the spring put together. And if we do that, then there are no external forces, right? The force of the spring on the train is an internal force. It's internal to the system. So it's not going to do any work. And actually, there's no change in energy from situation A to situation B. Right? All we're going to do is we're going to change how we arrange the energy, but we won't be changing how much energy there is. Yusuf, if you really want to see it done with calculus, we can do that in a minute. How would we know if there's a change in energy? So there can only be a change in energy if there's an external force. So if there's no force from outside the system, the energy of the system, the total energy of the system can't change. So it's a shift in perspective, right? So chapter 4, 5, 6, we're like, oh, forces are things that cause accelerations. Wonderful. In chapter 7, our perspective is actually, oh, forces are things that do work and change the energy of a system. And in next chapter, in chapter 8, we'll take the perspective, oh, actually, forces are things that change the momentum of a system. And all three perspectives are true. It's just a question of which perspective is useful to us at a particular time. Okay, so in this particular way of drawing the system, there's no external forces, so there's no energy change. That lets us say, well, the energy at situation A must be the same at the energy at situation B. And then we just have to write down what kinds of energy we have at each situation. So what kind of energy do we have in situation A? So at A we have potential. And what kind of potential, right? Let's make a little note. We know about kinetic energy. It's 1/2 mv squared. We know about gravitational potential energy, mgh. And we also know about spring potential energy, 1/2 k delta x squared. So yeah, on the purple picture, the train is moving, so it has kinetic energy, but that's it. And at situation B, it's not moving, but we do have a squished spring. And they're asking, what's the force constant of the spring? Well, okay. So solve for K. K is equal to, the halves cancel, mv squared over delta x squared. Okay. And then we just have to, do this math. So we've got, in the numerator, we've got 3 factors of 5. So that's 125. And in the denominator, we've got 2 factors of 4. And then when we go to count factors of 10, in the numerator, we have 5. And then 2 factors of 10 to the negative 1. So that brings us down to 10 to the 3. And then we have 2 factors of 10 to the minus 1 in the denominator, so that brings us back up to 10 to the 5. And if all of our units are SI standard, right, meters, kilograms, seconds, and we do this what did I do? We do this calculation, it should come out in newtons per meter. Does that answer your question, Jasmine? You feel all right about that?
Yeah, definitely. Thank you.
You're welcome. All right. Yusuf, you want to do an integral? It's not that exciting an integral. If we remember our calculus class, instead of saying that work is F times delta x, we actually say work is the integral of F dx. So in this case, the force is being provided by the spring. So we have kx, right? That's the force, dx. And the limits of our integration here will be from 0 squish to 0.4 squish. So our work will be equal to, right, integral of kx dx is 1/2 kx squared, and we evaluate that at 0 and 0.4. And then on the other side of this, we say, this work must be equal to change in energy. But since we're only considering just the train to be our system, the change in its energy is its change in kinetic energy, which is equal to, right, it loses, it loses, 1/2 mv squared worth of energy. Yeah. And then we solve for k the same way. We get exactly the same thing. Faster? I would not say faster. It is more flexible. Right? So the green method can only consider situations where the magnitude of the force doesn't change, where the direction of the force doesn't change, and where the path is only a straight line. The orange method can consider curved paths, can consider varying forces. So that's way more flexible. But for situations where they both apply, I wouldn't say it's faster. Well, in this class, we're not going to use it at all. And unless you decide to switch from pre-med to engineering, right, you'll probably never see it again. But notice, from A to B here, right, our situation, our velocity is not constant. Our speed is not constant. Right? We've gone from 0.5 meters a second to 0 meters a second of speed. So, and our acceleration was not even constant, right? Because our acceleration is going to be caused by the force, right? Negative kx, and x is changing. So that actually, that's an illustration of why work and energy is in some ways a much more powerful tool than kinematics, right? So the kinematics we developed in the first couple of chapters, we could only deal with situations where the acceleration was constant. Now that we have energetics, right, we actually don't care what the acceleration is. We care what the situation looks like at A and what it looks like at B. We don't care at all what happens in the middle. Does that make sense? Yeah. So, yeah, we in fact don't even necessarily care about that. Like, we can calculate the energy at A, the energy at B, and if they're different, then we must conclude there was a non-conservative force involved. And in this class, I think the only non-conservative force we're going to deal with is friction. Right? So friction is always going to be trying to steal the kinetic energy from a system. It's going to take that kinetic energy and morph it into heat. Right? It's going to heat up the surface that it's skidding over. But yeah, in fact, do you guys want to see my favorite problem from the whole semester? Because we've got the tools to deal with it now. Okay, so I mean, I have a favorite problem from every chapter, but this problem is my favorite from the whole semester. Right? It's my favorite thing ever. Alright, so I don't like roller coasters, but I have played a lot of Planet Coaster. So say we have a track that goes something like this. We start off on a hill, we make a loop, and we go on. we start off here. And the big failure point for this roller coaster is when you're on the top of this loop. And I know this looks a little bit like problem 10 from the exam. So the question we want to answer is, what is the relationship between the height of the hill and the height of this loop? If we don't want our roller coaster to crash. Don't spoil it. I mean, Yusuf is correct, but it's the journey, not the destination, man. All right. So we have two situations: top of the hill, top of the loop. And we want to combine an energy analysis and a force analysis. So we'll do the force analysis first because it basically is question 10 from the exam. So if the cart is at the top of the loop, its weight is pulling down on it, and the normal force between the track and the cart is pushing down on it. So sum of forces in the y direction at B is, and here we'll say that for convenience, we're going to say that down is the positive y direction. Well, no, that we don't need to. Okay. So the forces are minus n minus mg, and because the loop is basically circular, we know that this has to be equal to mv squared over r. Right? If it's not equal to mv squared over r, then the people in the cart are going to have a bad day. They're going to be falling off of the track, and there are going to be many, many lawsuits. So, just like on the exam, you were asked for what's the minimum, like you were asked for the minimum speed, right? And the way we think about that is, well, on the left-hand side, the weight can't change. The weight's constant. But the normal force could get smaller and smaller. And if we imagine a situation in which the track is barely connecting with the cart, that corresponds to a situation where the normal force is 0. So we get minus mg equals minus mv squared over r. Minus m is going to cancel from both sides, and we can get v squared is equal to gr. That ends our force analysis. But then we can jump back over to the left and start thinking about energy, right? So the work done from A to B is going to be 0, right? There's no external forces, right? There's no rocket engines on the cart. There's no magnets at play. There's no anything, right? So we expect energy to be conserved from A to B. Which lets us say that actually the energy at point A is going to be equal to the energy at point B. At point A, what kind of energy do we have? Yep, we just have potential energy. Gravitational potential energy, in fact. So we have mgh. That's the energy we have at A. What's the energy we have at B? We do have kinetic. Do we also have potential? Yeah, we do have potential because we're actually a height of 2r above the ground, right? We're at the top of the loop. Will it pause at the top? No. If it pauses at the top, you are crashing. But this point up here, right? The distance between the ground and that point up there is twice the radius of the loop. Our force analysis from before lets us take this v squared and replace it with gr. So we have mgh equals 1/2 mgr. That's supposed to be a plus. Plus 2 mgr. An m and a g cancel out of everything. And we get h equals 5/2 r. Right, so the height of your hill needs to be at least 25% higher than your tallest loop. So there we go. You're all now certified to become roller coaster engineers. We'll have to show that on a test. Why the frowny face? You've seen how it's done. Don't worry. This won't be on an exam, because I've held in reserve my second favorite work energy problem, and I'll put that on an exam instead. Sure. Yeah, if no one's got any objections, we can finish this off with Chapter 7, Question 20. Is this the problem you were asking about, Jasmine?
Yeah, it's that one.
Okay. So we have some Hot Wheel tracks. I'm kind of sad because my youngest just aged out of this toy. So we're not actually considering the case where the spring is compressed. So our situation A is going to be right after the spring is done speeding this car up. and its initial speed is going to be 2. Situation B will be the car up here at the top of this slope, where the change in height is 18 centimeters, and yeah, we want to show what its velocity is up there. This will be situation B. So once again, we're told it's a frictionless slope. So we're going to ignore that, which means that there's no external forces here. So the work done moving from A to B ought to be 0. So we have conservation of energy. So the energy at A should equal the energy at B. So what kind of energy do we have at A? Yep, kinetic energy at A. What kind of energy do we have at B? We do have potential, but the car isn't stopped, right? Yeah, kinetic as well. Alright, so we can cancel an m out of everything. And then maybe move this GHB term to the left-hand side of the equation. So one half VA squared minus GHB equals 1/2 VB squared. So multiply everything by 2. And if we want just VB instead of VB squared, we can take the square root of everything. So we get the square root of, initial speed was 2, so square of that is 4. And then minus 2 times g times the change in height. So this is like, so we have 4. Is it times or minus? That's a minus. Yeah. So 2 times 10 is 20. 20 times 0.18 is going to be 0.36. Or sorry, 3.6. So 4 minus 3.6 is going to be 0.4. And in fact, the square root of 0.4 is about 0.68. Oh, not 0.2. So maybe we pull a little trick in here, so that underneath the square root, we have 40 times 1/100, right? So we've multiplied and divided by 100 under the square root here. The 1/100 can come out and just be 1/10 square root of 40. And the square root of 40 is going to be between 6 and 7. So somewhere around 6.5. And then divide by 10. It's going to be like 0.6 something.
Dr. Wolfs, may I ask like 2 questions really quick about what we just did?
Of course.
Okay, so when you say like there are no like external force, like what do you mean by that?
So if our system is just the car, right? Between
Yeah.
A and B, there's nothing acting on it that could do work, right?
Like no friction and no gravity, I guess.
Well, gravity is part of it, right? So we are considering
yeah.
gravity as a kind of energy here. Right? But that's actually a good question, because we can actually consider, there's 2 different perspectives on gravity that we can have, right? We can either consider gravity to be a force that does work, or we can consider gravity as a source of potential energy. Right? And either perspective will give us exactly the same answer. It's just a question of, will we have an MGH? Will we have it in here, or will we have it on this side of the equation? Does that make sense?
Yeah, and also so like if there was friction, then we wouldn't say that it's like there. We would say that there is external force, right?
Right.
Okay.
But
And
since we have,
so
since we have friction on a curved track, right? We would have to use an integral to compute how long the track is, right? What the normal force is at every point, and then calculate how
okay.
much friction at every point.
So also about VB, right? So when you take the square root, usually it's a plus or minus. Why did you assume that's like positive?
That's an excellent question. Because you're right. The negative solution would also fulfill it mathematically, right? Because whether you're going to the left or the right, you would still have the same amount of energy, right? But if it was negative, what that would mean is that at some point you stopped and then started rolling back down the slope, right?
So we're considering like the direction in the like we're just considering the x direction. We're not considering the y direction. When we're thinking about like positive and negative.
Yeah, and because of the way we've situated this, we actually, the positive direction is just whatever direction the car is traveling at that moment.
Okay, so we're not thinking about the y direction at all.
Right, because the car is not going to, well, I mean, so I'm not thinking about the y direction at all. Not really, right? So, I mean, your initial question was, why don't we choose the negative sign, right?
Yeah, well, I mean, just like if like maybe if we were going down, maybe like like what if we were going down? Would we still say velocity is positive?
So, let's imagine there were like 2 hills here, right?
Yeah.
So you come up the first hill, and coming up the first hill, you're going to slow down to 0.8687 meters per second, right? And then let's say you don't make it up the second hill, right? You stop here, and then you start rolling backwards, right?
Yeah.
So if you were rolling backwards at this height, you would still be rolling backwards with the same speed. You'd just be headed down the slope instead of up the slope.
Yeah, so with these problems, we should just think about like the ones with the hills. We should just think about like the x direction. We shouldn't think about like the y direction, I guess. That's what I'm saying.
Well, so when we're considering energy, energy doesn't actually care whether it's the x direction or the y direction. All that the energy cares about is your total speed.
Right, but we're talking about, we're trying to find like velocity though. That's what I'm, yeah. So if like with velocity, because we took the square root, right? And if with velocity, like when we take the square root, it's either like a plus or a minus. So when we're doing like problems like that where we have to find velocity and we're doing it like we're doing it for like problems that we're like on a like we're like problems that deal with like hills and stuff. So we would just consider the x direction like to determine the whether velocity is positive or negative, and not like look at the y direction to determine that.
So what I'm trying to say is it doesn't matter. Right? So if we're doing our energy considerations over here, you notice that none of these terms have any reference to the x direction or y direction
Yeah.
because they don't care. Right? It's like so remember a minute ago I was saying like when we consider energetics, we care about where we started and where we ended up. We don't care at all about the middle parts, right?
Okay, so if we were like, let's say if we were going downhill and I said negative, right? Would that be acceptable?
Sure, because that's like that's also, I mean that's also a physically acceptable situation. Whether you're going up the hill or down the hill, as long as you're at that height, you will have the same speed.
Okay. Alrighty. So so sorry, just to make sure one more time. So if it, like, let's say if I pretend that I was going down the hill and I said negative velocity, I'm like okay, even though it might be moving from left to right.
Yep, that's fine.
Okay.
Although you will
Thank
notice
you.
in this question, they very carefully say speed, not velocity.
But if they did say velocity, then would that be okay?
Yeah,
Okay.
yeah. So
Thank you
energy
much.
doesn't care which direction you're moving; it only cares how fast.
Okay. Thank you so much.
You're welcome. All right. Well, I think we've had a really productive office hours sessions. Everyone feel good about today's work?